Cool. Hi, I am Nabeel Syed from eBay Network Engineering,
I'm Guru Harakere from Broadcom.
and today we'll be presenting something practical and near dear to your hearts if you're an operator. And it's going to be a testing and simulation framework to roll out SONiC at scale. So let's get started. So network testing, right? As an operator, the network testing is a challenge if you want to do it at scale. So if you want to build out a lab, a physical lab is expensive. You need obviously the gear, the optics, which are pretty. It's a very varied and fast-changing landscape for optics. So those are pretty costly, and then labor, obviously, types of cabling. So a high dollar cost associated with the physical lab, and because of that reason, it's low ROI, right? The physical lab is also very static. You can't really move cabling and stuff so much without obviously help from your data center teams and so forth. So it's static. Expensive, and not conducive to quick testing and rolling out software on your network nodes at high speed. On the other end of the spectrum, you have just pure software control plane testing, right? So that you could do with just routing daemon like FRR or Quagga. You can test that, but obviously that's very limited, right? So you can only test your control plane with that. So ultimately, what you have is a high cost and slow velocity of testing. So obviously, at this point, we're presented with this question of, is there a way to improve this, and to do some sort of unmanned testing at some speed, and if not in a holistic way, but at least to speed up testing so that you can narrow down some candidate images, for SONiC to deploy, and then take your testing on, over to the physical side and do that bit, right? So that's our problem statement. Now, testing as a whole in the bigger scheme of things, testing, as you see on the right-hand side, is mainly software, right? Other than the hardware layer at the bottom. Everything else on top, your kernel, your SI, your ASIC SDK, and everything, SONiC and above, the applications and the containers, they're all software. So most of SONiC testing and network testing is software related. So if you can speed that portion up, you're ultimately speeding up your testing. Just the virtual NOS, if you're just running SONiC VS, or virtual SONiC, that obviously is limited. You can do this. You can do your control plane, your routing, your containerized applications, and the NOS, right? But nothing else. So that's limited also. The hardware components. Now, if you think about it, those are pretty hardened already, right? So your ASIC obviously is tested. All the specs are published. And how often do you see your ASIC specs are not way out of line, right, in terms of number of routes you can program and so forth. So those components are already pretty hardened. So not to say obviously that you don't need to do hardware testing. You still need to put everything together, in the types of cabling you're selecting, your optics, your rack deployment pattern and everything. You have to sort of test the whole package. But hardware components are already pretty hardened. That testing is usually independent of scale. So if you're testing for performance, for QoS, congestion, and things of that nature, you need one box, with a traffic generator, or two at max, right? And you can stress that box, right, as a hardware. But if you want to scale it up and scale things up to some sort of scale that resembles your actual production network, or even a subset of that, then you need to go virtual. And there's really no other way other than if you're concerned about cost. So in this slide, you'll see a snapshot of the types of testing we do that I think pretty much everyone does. If you're from an operator perspective, and the options available for testing, right? So you have device qualification, what we call device qualification, which is basically where you select a model of a type of specific platform for a given role or a new role. If you have a new role, and you want to see if the gear is up to par, right? And then design validation would be putting that gear in a specific part in the topology, and then all the other nodes in the topology, right? Can they work as a larger network fabric with your oversubscription that you desire, with the routing protocol that you want to run, all the other feature set. So that's the design validation part. And then code certification, a given topology, a given device, but you want to change the code on it because your requirements have changed, or you want to introduce a new feature, fix a bug, and so forth. And then network changes, which are I would say most changes people have SOPs, standard operating procedures, for those tests, for those changes. But then you have some changes that can be a little bit non-standard, non-routine, but more complex migrations and things of that nature, where you do want some sort of a lab to test that before you deploy it. So these are the use cases, and then the options available, right? So you have routing, daemon, FR, right? So you can do routing, but you obviously can't do a lot of the other stuff, right? So and on the right hand side you have the physical hardware. So physical obviously can do all of those things, but at a high cost, right? It's not scalable, right? So the sweet spot for us, using Broadcom's chip simulator, device simulator, is that that basic option is where you could test a lot of those things to a great extent. The software and down to the SI and SDK, ASIC SDK, drivers, and basically knock out a lot of the software testing, a lot of the bugs, and then maybe move on to the hardware and do the remaining over there. So it's a good compromise, right? The last two options, lets you do a lot of the testing without the associated cost, and the cost doesn't scale exponentially. So I'll hand it over to Guru.
Hi. Thanks, Nabeel. So the use cases have been laid out. Let's look at what options we have in SONiC, right? On the left side, that's your typical hardware. You have a Broadcom device. You have SI, and obviously, as Nabeel stated, its scaling is it's very costly. And the second problem is also, if you want to automate some of these tests on our hardware, it's not that easy, because you have to go move the racks, put the cable, and so on and so forth. So so that obviously you have to test some portion on that, especially performance and that kind of tests. But we do have something already existing in the SONiC ecosystem, which is called the SONiC VS, which doesn't really do the data plane as the chip does, but it does has most of the functionality. It's a pretty awesome tool that we can use. In fact, internally in Broadcom engineering, we use a lot of SONiC VS. It gives you a good control plane and management coverage. It's scalable because it's all virtual machines, so you can put in cheap servers and expand your network, and also low TCO. However, what Nabeel's sweet spot, or eBay's sweet spot, was that it needs to use the Broadcom simulator, right? So we need to build something different than SONiC VS. So on your right, if you look at the overall stack of vSONiC, or the virtual SONiC, just to put the name as vSONiC just to differentiate between SONiC VS, is a SONiC image that runs on Broadcom simulator. This is the same SONiC image, or at least 90–95% the same SONiC image that you run on the hardware. And within the SI SDK, we have a switch that can make it work on the simulator, or it can work on the hardware. So that way, you can build it to two different versions with just that compile time fly, or you can also make it very dynamic. That is, you can run the same binary that you run on hardware, and it let some properties to figure it out whether it's running on the simulator or not, right? So this seems to fit all the requirements that Nabeel is talking. But simulators are slow, and especially if you are looking at a very cycle accurate simulator, which exactly emulates how the chip behaves, there are a lot of overheads in processing, right? the device initialization itself could be very slow. So by the time you get to system ready, it could be 3-4 minutes or even 5 minutes, right? Secondly, in the packet path, since all the simulation cycles are serial, so it has to do one at a time. That means it processes one packet at a time. But if you're doing some programming, then that's done, and then this is done next. So a lot of things are very serial in a Broadcom simulator, and we are talking about scale here, right? So, and then with all this, if you just build a scale of BGP network, simple BGP underlay, the actual protocol control plane traffic itself can overwhelm the simulator because there's so much of packet exchange that happens within the network without any data traffic. So given all this, how did we design VSONiC? So one of the things, let's look at the VSONiC as it is, and then let's see how we optimized it, right? On your left side, let's look at the control plane part, because that's where, even to get the system stable, we need to address the control plane chattiness, right? So if you look at the hardware, the path is when the packets enter the Broadcom SOC, it's punted to the KNet driver, the control plane packets, and then it goes to the Linux stack and then to the applications. So when we have VSONiC, there's no PCI device, so there's no KNet driver. So we had to build a UNet, that's what we call, that will interact, replaces the KNet driver, and it fields all the control plane traffic. And then, and beyond that, everything else is SONiC application. So UNet is a part of SyncD, and so the applications above running, they don't even have an idea that they're running on a simulator. So that's how we stacked it up. However, the default mode of VSONiC with the default simulator is very slow, and I'm going to show you some data later. However, given that as a problem, we looked at the requirements they had. It was a pure, simple BGP underlay. So we thought that if we can bypass or offload all the control plane directly to SONiC instead of sending it through the simulator, because what the simulator is doing in the control plane is just sending it, if it's my packet, my MAC, it just points it to the CPU. So there's no point in spending the simulator cycles just for doing that. So we built a filter, which is a smart, quick look up into the packet. It figures out if it's its packet, its MAC, and then it just sends it to SyncD directly, or the unit driver. Now, given that everything is in user space, so we're able to find out, auto-configure all the MAC and other things. So we can, all these things are, it's just seamless. So here is a comparison of with and without bypass. Now, if you see on the y-axis, it's a ping round trip time just between two nodes with three variants. One is SONiC VS, one is VSONiC in default mode, and one is VSONiC in control plane, right? The lines on the x-axis, you can't even see the SONiC VS latency, right? It's in less than 10 milliseconds, right? But if you look at the red line, all it's showing you is the minimum is around 50 to 60, average is around 250, and sometimes you get 800 milliseconds. There's no way you can scale in the default mode for VSONiC, so it has to be the bypass. So we did one more test with the bypass mode where we start programming the chip, on the chip meaning here the simulator, and then we also induce some control plane traffic and see if the bypass actually survives this test, right? And as you can see on the y-axis, we are programming 10K routes, and it's the time taken to do that. On the x-axis, we have time measured for multiple instances of ping, just to induce some control plane. And then on your right, there's the ping latency in milliseconds, right? So when all these things happen together, you can see that the 10K routing, which is in sort of green and yellow, it's always consistent. But the blue one, the time starts increasing as you add more ping sessions to it. And you can see the graph of ping latency. That's almost, it's about 100,000 milliseconds. So obviously, the bypass mode was a solution that we could offer. We internally tested this. We could scale up to 60 nodes, and then we were confident that we could give that for eBay to try it out. And I'll give control back to Nabeel to share his findings. on
All
VSonic.
right, so we have a demo for you, a video demo. So this is, I think the demo goes over the diagram itself. So I'll leave that up to the demo. The testbed itself, right? So testbed was pretty simple, just two machines, a previous gen, not the latest and greatest that we have, but it does not require a lot. Up to 92 VSonic nodes is what we were able to spin up. With 100% CPU on both. So if you reduce that by half, we were seeing like 50% CPU on each machine. And if you take that into scale, you could scale up to 1,800 nodes in a single rack. So that's, if you're not a hyperscaler, that's a pretty good scale that you could use to test basically all your nodes. So we'll go over and response times. Average response times. The topology was no more than 3 hops, maximum distance from any two nodes. So average latency, you can see 50 to 75, milliseconds pinging devices in there. So let's do the demo now, if I can get this going. All right. I don't think I have audio. Oh, here.
Can you switch it? You have to switch your. You have to go out of your
Yeah, no, I think I did that. Let's try that. All right, there we go. Okay.
This is a demo of eBay's virtual SONiC topology using Broadcom's VSonic chip simulator.
The audio is not, the video is not showing up.
I think you have to go out of your presentation mode.
Oh, this one, yes. Okay,
Yeah,
that's better. Thank you.
The topology comprises of 4 clusters of spine and leaf
So
switches
no,
connecting to an aggregation.
no video here.
This
Okay.
is a demo.
Trying to play the video?
Yeah.
Of eBay.
It's not coming, presentation.
Well, it's VLC. I'm not sure if there's any special setting here.
Virtual SONiC.
I think for the sake of time, why don't you just talk about it and we can
Yeah,
upload it
well,
later.
I some visuals to the show, but
I mean, the screen is visible. Do you want to try the icon? The VLC one. Yeah.
Make it smaller.
small.
Oh,
Move it around.
yeah,
Ah, here we go.
Yes.
Okay.
Yeah.
It's as if there's
It
two
was
screens,
hidden
it's only one,
somewhere.
but there's nothing showing up there.
Network deployment.
Yeah. Oh, here we go. Okay.
Supporting an independent
Let me see if I can
compute
speed this
allocation
up.
footprint in the eBay production network. With the exception of the aggregation layer, all nodes in the topology are VSonic nodes. The topology spans 2 bare metal machines and runs 92 VSonic nodes as QEMU VMs using approximately 6 gigabytes of RAM for each VM. The CPU load on the host machine is commensurate with the number of nodes or VMs being simulated and the aggregate control plane load of these VMs. Here's a closer look at one of the nodes in the topology. The on-chip simulator uses the same SONiC binary as the physical hardware. The physical platform model virtually is an Acton 32-port switch. The control plane runs the familiar Docker containers. With the chip simulator modeled inside the SyncD container. using one full virtual CPU per VM for the process itself. Here's a look at the interfaces and LLDP interacting with the kernel space and discovering other VSONiC nodes in the topology. Let's take a look at the routing control plane. Here's a dump of the routing table with all prefixes learned in BGP from the virtual topology itself, with the total number of prefixes. Critical resource monitoring, or CRM, reflects the current scale of the control plane as learned from Syed. Let's get inside the ASIC shell to take a look at the ASIC programming. Here's a look at the ASIC physical port representation with the link state, STP, forwarding status, and other useful information. Here's a look at the interface counters as recorded at the ASIC level, providing validation for packet flows not possible using control plane only SONiC models. A look at layer 2, not many MAC addresses for a purely routed topology and node. As for layer 3, here are the number of prefixes programmed in the ASIC, matching the CRM output shown earlier. Let's take a closer look at one of these prefixes. Here's the control plane output, showing the BGP next hop and egress interface. Now let's find the same prefix in the ASIC. Let's find the same prefix in the ASIC, and here it is, showing the outgoing interface. And here's the L3 adjacencies table. Showing the same egress interface and associated next hop. Complete control and data plane validation without the physical hardware. We hope you enjoyed this demo. Thanks for watching.
All right. Well, last but not least, the call to action. So I think this was, we're just starting on this journey. We'll maybe give an update later on how it goes. But for us to really scale up and succeed, we need these kinds of simulators from all the chip vendors. So that's the way forward, and that will really enable us to adopt this as a strategy, as a serious strategy going forward. So that's it. Thank you.
Thank you.
Great.